Hey guys, today we're going to talk about emission spectra. So in the last video we talked about the different orbits and the different energy levels and how the electrons jump from the ground state to the excited state, and in order to do that they need energy to be put through them. And when they drop back down to the ground state, they release energy in the form of light. So emission spectra is that light, and we use it to determine composition of different samples of elements and substances. When the sample is excited, often by sending an electrical current through it, it gives off a distinct pattern of visible light. So when we see the emission spectra, we actually have to use a spectroscope, which can be a device or a tool, or it can be in the form of glasses. We are going to use both in class. This spectroscope is able to break apart the light and form these color outputs, and we see this distinct pattern of visible light. But what does this mean? All elements have a distinct emission spectrum. Bohr noticed that hydrogen always created the same exact pattern every time it was excited or electricity traveled through it. When the electron in hydrogen was excited, they always jumped to the same energy levels, meaning that there has to be energy levels or orbits present. So this emission spectra, this diagram at the bottom of the slide, this is hydrogen's example. And notice there's a purple, an indigo, a light blue, and a red line. Every time hydrogen becomes excited, this spectrum is always created. But what about other elements? The more you move to the right of the periodic table, the smaller the atomic radius becomes. So remember, as you move left to right, the attraction from the nucleus and the attraction from the electrons in the electron shell increases, and those electrons actually move closer to the nucleus. And the closer the electrons orbit, the more sporadically they can jump, meaning they're less predictable and there are more lines. So I always like to compare this to the game of the floor is lava. If you only have one or two pillows and you have to move across an entire room, you have a specific pattern that makes it easier. So maybe you only have 2 jumps to get to the opposite side of the room. But as you add pillows, if instead of 2 you now have 15, you have multiple paths you can take that can get you from point A to point B. Electrons do the same thing. The closer the orbits get, and the more electrons that are present, the more jumps they're able to create. So we can have multiple colors and multiple lines of each color visible in the emission spectrum. So here are some examples. Lithium is the top example, and notice we have 1, 2, 3 distinct lines, and maybe 3 more slight lines. Sodium is directly underneath lithium, and we go from having 3 electrons to having 11 electrons, and we have a lot more line possibilities. Potassium is the next one down. Again, we have lots more lines, then rubidium, and then cesium. So the issue with this first column is it's almost a catch-22. We have more electrons as we travel down, but rubidium and cesium also have larger radii. So even though there's more possibilities of items to do the jumping, you have less areas to jump to. So the second column, these are the alkaline earth metals, and we have beryllium through barium. And again, notice lithium to beryllium, we have more lines because we have more electrons. We also have a slightly smaller radius, so there are more lines present. Beryllium down to magnesium, same pattern. We have more electrons, but a bigger radius. Magnesium to calcium, calcium down. So again, as we get to the bottom, we have more electrons, but less areas for them to jump because of how difficult it is to jump the large radii. So as we move to the right of the periodic table and we get to fluorine, chlorine, and even the noble gases, we increase all of these lines, and there are a lot more distinct lines present because now we have a denser radius, the electron shells are closer together, and we have more electrons to do the jumping. So when I see you in class, we're going to be using the emission spectra in order to try to identify and characterize some elements. So we are going to use spectroscopes in the back room as well as with overhead lights and sunlight and see what differences we notice and how we can use those in terms of chemistry. So I'll see you then.